I'm going to talk about how to attenuate for successful beam profiling. A lot of emphasis is given upon the sensor and the type of profiler, but actually sometimes underrated is how to attenuate the beam to get best results. A beam profile is a measurement of the power distribution of the beam in space. And so if you look on the right-hand side, you'll see this sort of donut. Donut happens to be a carbon dioxide laser used in a cutting system, like cutting of sheet metal. When people look at beam profiles, they want to know usually what the size of the beam is, where the position is, how stable is that position, is it moving, is it stationary, as things warm up, is the beam moving, or is it fairly stable? Optical curing, where you're curing to lock optics in place. As the curing dries, that can change the position of some of the optics. Beam quality, mode structure, how good is this laser, how focusable is it, what sort of power distribution am I delivering to my target, and general questions about the beam shape. So oftentimes beam profiling is described as a snapshot of the beam. We're looking at how the power is distributed, because how the power is distributed is basically tells you how the laser is going to work and how your optics are working. This is why beam profiling is comparatively hard. Common ways to diagnose lasers are using power meters. Power meter is much more simpler than a beam profiler. Basically, you have a sensor disc, and typically these discs can handle 10 to 50 kilowatts per square centimeter. And you just direct your laser onto the thermopile disc. These are fairly common in the photonics industry. And out comes your reading of how much power you have. At lower powers, you can use photodiodes. But again, they can pretty much handle a fair amount of power. So you can basically just direct the beam at the sensor, and you don't really have to worry about attenuating it or anything. You can just, as long as the beam is large enough, you'll get a reading. Well, you can't do that with most sensors used in beam profiling. If you look at the bottom right, that's a CCD array, focal plane array sensor, and it saturates at 1 microwatt per square centimeter. That's over 10 orders of magnitude from typical power sensors. Basically, if you were going to measure power using the thermopile disc at the upper right, and you also wanted to measure profile of that same laser, you would have to attenuate the beam about 10 orders of magnitude. That's 10 billionths. A big part of successful beam profiling is about attenuating the beam without disturbing the integrity of the profile. You're basically throwing away almost all the laser power and just looking at a little piece of the beam. Typically, what a beam profiling involves is both a sensor to detect the light and an attenuation scheme to prevent the sensor from being saturated or even damages. And this basic scheme has led to two main classes of beam profilers. One is a focal plane array profiler, sometimes called a camera sensor, consisting of pixels etched into a semiconductor material. And so the beam attenuation is done optically. Some sort of filter to either an absorptive filter, as we'll see, to reduce the beam power, reflective attenuators to reflect much of the beam power away. But it's some sort of optical scheme to reduce the beam power. Small amount of power that gets through that attenuation scheme gets to the sensor. You can get a reliable profile. The other method is basically some sort of scanning aperture. And so what's used is usually a single element detector is used in conjunction with a scanning aperture. The aperture basically blocks most of the beam, only allowing a little bit of that beam to get through to the sensor. And essentially, beam attenuation is done mechanically. So then I'm going to go into examples of both optical and mechanical beam attenuation. So this is an example of a focal plane array profiler. The ones that are most commercially available are silicon, which operates typically from 266 to 1100 nanometers, generally in the visible and UV wavelengths, and some near infrared. And then in-gas profilers typically work from about 800 nanometers up to 1800 nanometers. There are different materials. There's certainly other focal plane arrays using different semiconductor materials that handle different wavelengths, but those are the two main ones that you'll run across. Generally what happens is the sensor inside that profiler will saturate at 1 microwatt per square centimeter, a much lower power per unit area than most lasers are generating. So there's some sort of front-end optics required. In this case, you can see a filter on the front of that profiler on the right-hand side to generate a 2D representation of the beam. And as you see below, I don't recall exactly what this laser is, but that was a beam. It's pretty ugly looking. In this case, they didn't need a very high quality beam for what they were doing. This will generate various 2D representations of the power, where the red and the yellow regions are warm, using warmer colors to sort of express the fact that those areas are hotter. There's more power per unit area than the cooler colors, greens and light blues and purples, where there's less power per unit area. This types of information from these profilers tells you kind of the shape of the beam. In this case, it's kind of an irregular blob, and also indicates that you have some hot spots sort of in the middle. That's the type of information that you would get from a profiler like this. A scanning aperture profiler uses knife edges, slits, wires, other physical objects. Usually knife edge, slits, and wires pretty much cover most of them. Focal plane arrays are mainly a development of the 80s and 90s. They're somewhat ubiquitous today, but back in the 70s, that's when laser barcodes started being introduced in grocery stores. Laser printer development started in the 70s. There was certainly a need to profile lasers. Since you didn't have array profilers back then, you take some sort of scanning aperture and pass it through the beam. What advantage is you can make a fairly small slit. You can make them as small as 1 to 10 microns, allow a very small amount, a very small piece of the beam to pass through that slit onto a detector. You actually can measure most beams without attenuation, and you can also, if you have a very fine encoder and you can determine the position of that slit very accurately, you can actually measure fairly small beams down to 5 microns using this technique. So they do have some advantage over camera profilers because you're measuring the beam through a slit or a knife edge or something that doesn't give a full 2D representation. You do lose some spatial information from the beam because, for example, in the slit, the light can come through the top of the slit or the bottom of the slit or the middle of the slit, and the detector on the other side of the slit, as you can see in the upper right-hand side, it doesn't really care where the light comes from. It just measures all the light that comes through the slit. Sort of a disadvantage of a scanning aperture profiler is there is a loss of spatial information based on the technique it uses. So if you're using a highly multimode beam or measuring the multimode character is really important for your application, scanning apertures do pose some problems. So the next thing I'm going to get into is understanding the application. What are the things you need to be aware of and address when you're trying to characterize your laser, how they'll affect how you need to approach the measurement. So the important things to understand are the wavelengths, the beam size that you want to measure, is the beam continuous or pulse, and if it's pulse, what that pulse frequency is. Then this is the general case, how do you plan to use the beam profiler? What information are you looking for? Are you trying to look at focus? Are you trying to look at quality, position stability? Those can all factor into your choice of how to measure it. And of course, average power of the laser is an important characteristic because we have to attenuate it. So specifying the application, the wavelength determines what sensor the beam profiler uses. And so common beam profiling sensors are silicon, which covers the 266 to 1100 nanometer range. That's mostly visible, UV, and some near IR wavelengths. InGaAs, as I mentioned, 800 to 1800 nanometers. And then germanium also covers basically that same type of range. Pyroelectric crystals can cover well into the UV and millimeter wavelengths. Crystals that respond to heat by creating an acoustic signal. Any sort of heat, pyroelectric crystal will respond to. Bolometers are mostly a heat detector, tend to be much more sensitive than pyroelectric crystals, therefore require a lot more beam attenuation and sometimes can be very tricky to use in a beam profiling application because they're so sensitive to other heat sources. Your laser is a heat source, of course. A cup of coffee you set down next to the beam profiler is also a heat source that a bolometer will certainly detect. So, bolometers are used in profiling, but a lot of care needs to be used because they are so sensitive. Phosphor coatings on silicon, you can put various coatings, oftentimes that will glow through a 2-photon process at 1550 nanometers, which is typical for a lot of optical communications. You can create coatings that will glow in visible wavelengths, and then material glows and it's coated on the silicon. The silicon array will detect it. You can use different phosphors at different wavelengths. And then also UV conversion crystals are typically used at UV wavelengths. There's various crystals you can use, usually with some sort of dopant involved, that will glow at a visible wavelength when exposed to UV. And then you can image the visible light and profile that image. Beam size, you want to know the size of the beam. Beam profilers will cover different ranges of sizes, and so you want to make sure that the profiler you're using to characterize that beam will get the results you're looking for. Typically with a focal plane array, you want the beam size to be larger than 10 times the pixel size. So if you have for example, 100 micron beam, you want to make sure the focal plane array has at least 10 micron pixels in order to get a reliable profile. The other thing is scanning apertures. The beam size range will depend on the size of the aperture of the profiler and also the accuracy of the encoder. Sometimes you can use beam magnification or reduction optics if the beam is too large or small, is larger or smaller than the range of your profiler. And in some cases, there's a lot of reduction or magnification optics that you can use to expand the beam or reduce its size. Average power, that gets into understanding the level of beam attenuation needed. Focal plane arrays almost always require beam attenuation. The scanning aperture profilers often do not need a beam attenuation. Sometimes they do, depending if for very high power applications. Again, one of the strengths of scanning aperture profilers is they can handle a number of different lasers used in photonics without any additional profiling. So they're sometimes very easy to use. On the other hand, if you are using a scanning aperture profiler in a high power application, you typically will need some additional attenuation to prevent damaging the profiler. There's basically two types of optics used in beam attenuation. They're reflective attenuators, which do not thermally lens. You're basically reflecting the light on the surface of the attenuator, and so most of the light doesn't actually heat up the optics. And then absorptive attenuators, which can thermally lens. And this is very important when you're using any sort of filters, absorptive filters. You want to make sure you're not thermally lensing. And what thermal lensing is, it occurs when the filter locally heats during absorption such that the local index of refraction of the material changes, creating a thermal lens. And what happens is this will make the beam look larger than its true value. At high powers, you want to use reflective attenuators in front of absorptive ones to bring the beam irradiance down below the thermal lensing limit before using any absorptive optics. But just to go in further detail about thermal lensing, on the right is a chart that shows the thermal lensing limit. This is a bit of a conservative number that if you have more than 5 watts per square centimeter and you direct that beam onto a absorptive optic, you're probably going to create a thermal lens. Threshold is probably a little bit higher than 5 watts per square centimeter, but to be on the safe side, I just use 5 watts per square centimeter as a good rule of thumb. And you want to be careful because and I've seen this done, you simply can't just stack up a bunch of neutral absorptive filters to attenuate the beam. What will happen is the beam will look very large. I've seen this done before. It's basically a beam that was fairly small turned into a large blob, and it just really wasn't getting any real useful information. There's a chart on the right indicates the size of the beam and the measured power. Even if the beam is fairly small, a few milliwatts, you can still get thermal lensing if the beam is small enough. So there's definitely something that you want to keep in mind and take care to avoid, because if you do have thermal lensing, your beam will look larger than it really is when you profile it. Neutral density filters, by the name neutral density, they operate over a broad wavelength ranges. The chart on the right shows the different level of attenuation per wavelength. They're fairly broadband. Most filters are fairly broadband, but you do need to keep in mind that they can have some dips, and they may, depending on the wavelength, they will attenuate a little bit differently. If you're using neutral density filters, you want to make sure you understand how they'll perform at the wavelength you're operating at, because there is some variability in the filters. Reflective attenuators, you can use beam splitters. Probably the most common way, or what I find works the best, is to use a front surface reflection from a wedge optic. You can also use anti-reflection coatings to reduce the reflected power. And if you reduce the reflected power, you're increasing the beam attenuation. When you shine a beam that's coming from the left on that diagram on the right, you'll get a front surface reflection that you'll use to profile. And then you'll also, as the beam passes through the optics, you'll get a backside reflection, which will come back on the other side. First, you want to make sure that when you're profiling the front surface reflection and not the back surface, because the back surface reflection will be altered a little bit by the material it's passing through. And the second thing you want to realize, you have a reflection coming back, and you want to, in some way, block it, in some cases, a laser safety concern of any sort of back reflection. So this is the way the scheme usually works, and you want to just make sure you keep track of the beams and make sure you're profiling the beam you want. Also, when you do a front surface reflection, you will change the polarization of the light. And so what usually happens is these wedge attenuators are used in pairs with two front surface reflections at a 90-degree angle will maintain the polarization of the laser. So especially if you have a polarized laser, you want to make sure you're using this scheme in pairs to preserve the laser polarization. The focal plane sensor saturation threshold is typically 1 microwatt per square centimeter, and that's typically for the maximum exposure time. Most camera profilers have an exposure time adjustment where you can actually reduce the effective saturation threshold with 1 order of magnitude. Even if the beam power may be a little bit higher, maybe say 10 microwatts per square centimeter is the lowest you can get it down to. Typically, you can reduce the exposure time of the profiler to basically make the sensor less sensitive. And so what I normally just use is 1 micron as a good rule of thumb. But do keep in mind that typically you can probably go down without going all the way down to 1 microwatt per square centimeter to profile it. Irradiance can be calculated by simply taking the power divided by the area of the circle. Even though beams are not a uniform flat tops, that's usually a pretty good starting point when I'm trying to figure out how much beam attenuation I need to use. So let me give you an example. 2 milliwatt Heaney laser, 633 nanometers, 2 milliwatts. You do the math, that's 64 milliwatts per square centimeter. And we're well under the thermal lensing threshold, so we don't need to worry about thermal lensing characterizing this laser. And all we need to do is bring it down to about 4 orders of magnitude to bring the power down to the 1 micron per square centimeter saturation threshold. Basically, you can use up to 5 orders of magnitude of attenuation to bring the beam power down to an area where you can profile it. Here's an example of a similar laser. It's 0.5 milliwatt of power. It's CW. It's a 633 nanometer wavelength. It's about a 1.3 millimeter beam. This is actually a laser pointer. No one really cares too much about the optical quality of a laser pointer. They use fairly cheap diodes that are very multi-mode. The optics are very cheap. They tend to have scratches on them, so you can actually see that in some of the striations of this profile. So this is an example where you can actually see the structure of the beam and the elliptical nature of the beam through a profile. For example, the 2-watt beam at 532 nanometers, 100 micron beam size. The irradiance of the beam is 2.5 times 10 to the 4th watts per square centimeter. We're way above the thermal lensing threshold, so you cannot just put neutral density filters in front of a beam like this and expect to get a good profile. There's about 10 orders of magnitude required to profile the beam. What we do in this case is you can use 2 anti-reflective coated wedges that reflect only 1% of the beam. Each reflection is equivalent to ND2, reducing the beam by a factor of 2 orders of magnitude to bring the power down to the thermal lensing limit. Once you've brought the beam power down so it's below 5 watts per square centimeter, then you can use absorptive attenuation. And you can see on the right-hand side, the picture, this is something that we've developed. The beam comes in the top. There's 2 wedges inside of that block. And then if you see those 2 sort of red sliders with the 1 and the 2 numbers on them, those actually have absorptive filters. So the beam comes in, goes through a couple of front surface reflections that reduce the beam by a factor of 10,000, and then the absorptive filters reduce the beam power down further, so when the beam finally gets to the sensor of the profiler, it won't saturate or damage it, and you can get a profile, such as we see here. This is a beam profiler using the same scheme. This was a laser used in a welding application. The wavelength, it's an IR laser around 1 micron wavelength. This beam is about 100 microns. There's 70 watts of continuous power. In order to get this profile, we had to first use a reflective scheme to bring the beam power well down by a factor of at least 10,000, and then we used some additional absorptive attenuation so it would not saturate the profiler. On our website, we do actually have a means where we do this automatically, where you can put in your profile application and it will tell you what type of attenuator to use. For a scanning aperture profiler, you can think of the aperture providing only a small piece of the beam into the profiler, onto the detector. And so what normally is done is you can generate an operating space based on the beam size and input power to determine its operating range. So once you understand the operating range of a scanning slit profiler, you can determine whether or not you need additional attenuation. So here's a typical example of silicon scanning slit profiler that measures lasers in the visible. And you can see at the bottom along would be the x-axis, the beam size, and the vertical axis is the input power. So for example, if you have a beam, if we go back to our original example of a 2 millimeter Heaney laser, a few milliwatts, you can see that will fit within that parallelogram. So no beam attenuation is needed. If the beam would fall above the parallelogram, then you would realize that you would need additional attenuation to bring it into the beam power back into within that parallelogram, which is where the scanning slit profiler operates. And here's a typical example of a scanning slit profiler at somewhere between 1 to 10 milliwatts, in the visible beam size is about 120 microns. And because the slit acts as sort of a natural attenuator, it's very simple to simply point the beam into the profiler and out comes the profile. Why to go to this trouble? This is a customer I was dealing with. This is a laser welder. They were using a single shot pulse, and they were doing some laser welding of a medical device. Single shot, 1 millisecond, there's a fair amount of power, a fair amount of energy in a very short amount of time. So what we had to use is 2 reflective attenuators and then 2 absorptive attenuators before the beam got to the profiler. They were laser welding a medical device. They were having yield issues. The product was supposed to be producing a flat top, but it was not. It was producing this sort of chisel effect. You can see the red and yellow images where the hot spot was, and you can see almost like a crescent moon. That's not a very optimal profile to do welding. And so what they did is they worked with their laser vendor, good support, and the laser vendor gave them some suggestions on how to improve the quality of the beam. And then they were also able to characterize that. So when they started using different components, they actually rotated the laser rod and used a different pumping scheme. They were able to get a very uniform beam, as you see here. Their weld quality and yields went up considerably. They were able to save a lot of money and increase production capacity simply by characterizing the laser, attenuating it properly, and then able to look at the different ways they could improve their quality and actually, get metrics on how much better their laser was.
How do I verify that my method of attenuation does not affect the accuracy of the beam profile measurement?
As long as you follow these principles, using good optics, making sure you're not thermal lensing, making sure you're not clipping the beam. One way you can do that is simply to swap out optics and see if that changes anything. That would suggest that you might have a bad optic. You can change laser power sometimes. Some cases you can reduce the power where you don't need to use a reflective scheme and take the reflective attenuator out and see if that changes anything. It's something you do want to be troubleshooting. If you follow the principles that I've laid out and use good quality optics, you shouldn't run into any problems.
Why is the scanning aperture method bad for a multi-mode beam?
The reason why it's bad, I don't want to say bad, but there's a loss of spatial information. As you see on, I have the example of the Slit, but it's true for a knife edge, a scanning wire as well. What happens is the aperture goes through the profile, measures all the light that goes through. So if light goes through the top of the slit, the middle of the slit, or the bottom of the slit, wherever the light goes through the slit or through the knife edge or along the wire, that's what, and it's then directed to the detector, and it goes to the detector. That light is detected, and the detector will respond depending on where that light came from. And the difference is when you use a 2D array, whatever pixel the light falls onto in this 2D array, that's what pixel will get energized. So what will happen with a scanning aperture profiler, even though they're easier to use, if you have a very multi-mode beam or a beam with a lot of irregular patterns, that tends to get sort of washed out, and you've lost some spatial information because of the way the technique works, where the sensor will respond to all light depending on where it comes from. Things do not have to be purely Gaussian to use a scanning aperture, but if it becomes highly multi-mode and you're interested in the mode structure, for example, of the beam, you probably want to use a focal plane array rather than a scanning aperture if the two-dimensional structure of the beam is important to you.
Okay, why limit the number of neutral density filters to less than or equal to 3 in this 633 nanometer example?
You generally don't want to use large stacks of filters. There can be some reflections. They are optics. You will get some secondary reflections, and those filters are designed to minimize those. But if you have a very large stack of filters, start to get all sorts of reflections going on inside of them, and so generally you want to avoid having large stacks of filters. So we typically recommend not more than 3. I mean, you could use 4 and it might work okay, but you generally avoid adding a lot of optics into the path of the beam. If you have, for example, an ND3 filter, it's usually advantageous to use an ND3 filter than 3 ND1 filters. It's mainly to eliminate sort of extra reflections that could distort the integrity of the profile.
Will a beam go straight through a reflective neutral density filter if you angle it?
Yes, it will. It will go through the filter. If it can be angled slightly, it probably doesn't have much of an effect. It would depend on the optics and the actual index of refraction of the optics of exactly how it would behave. So
I think what he might be thinking about is like a multi-layer coating that would have varying reflectivity with angle. That's my guess is what he's trying to get at. But
okay, yeah, I mean generally the filters are designed for the beam to be go at a right angle to the filters. They couldn't handle a beam at less than a 90-degree angle, but then you do start getting into issues with what filters you're using that you do have to be careful about.
Can you scan the 3D spatial profile of a laser pulse?
With the extra dimension being time, it would depend on the time scale. It's possible. One of the things about a profiler is the update rates are typically like in the 10 to 30 hertz range. You can look at an evolution of maybe milliseconds, but that would be about as fast as you could, a few fractions of a second. But beyond that, if you wanted to look at like microsecond changes in the beam profile, that typically these CCD arrays, the update rates won't support something like that. There's higher speed cameras called like a street camera, but maybe you can do that kind of work. I don't know enough about street cameras, but for typical beam profilers, the update rates are typically like in the 20 hertz range. So you can't really measure a lot of very fast changing temporal changes to the beam. Interesting question.
How can you tell if your laser has a flat beam profile?
Flatness is kind of something you can measure, and it's actually what people do measure with beam profiles. You can actually characterize the flatness. Assuming you're attenuating the beam uniformly, you can look pixel to pixel and look at the RMS variation between pixels. And there's basically ways to quantify the flatness. And so if you're looking at what you're hoping will be a flat beam, you can actually use a profiler and quantify that flatness.
How do I know if I'm seeing thermal lensing in my absorptive attenuator?
So the thing about thermal lensing is it happens very quickly. So you won't see the beam slowly expand. It'll just be larger, and you won't even, it's a pretty quick effect. So the only really way to determine if it's thermal lensing is you can reduce the laser power, which would reduce the thermal lensing, and you can see basically if the beam is changing with power to a point where it reaches some steady state or something. As you reduce the power, you can deduce that you're seeing thermal lensing. But one of the things about thermal lensing is it's not something that slowly evolves with time. It happens fairly quickly. So if you're thermal lensing, you won't see it. It'll just happen instantaneous, which is why you have to be really careful about not having thermal lensing, because you can really make some incorrect conclusions if you have thermal lensing in your beam attenuation scheme.
What type of optics should I use for reflective beam attenuation?
Most commercial optics will work. You don't really need to have really high quality optics. I mean, typical like 40/20 scratch dig surface quality is sufficient. You can use better quality optics. We'll ensure a little bit better results. You normally don't have to get really all the best optics. Usually things that you can buy commercially off of typical websites that sell optics will be sufficient to profile.